Hello, this is team member for Plan for Plan. I'm Yinghua, and in this video, my teammate Zixing and I will present the two AI agents we developed for this reverse exam. Our first AI method is Minimax with alpha-beta pruning that uses heuristics to guide the agent to select the most promising action. The main point throughout the development was measuring the heuristics, which our final version comprised of the corners, current score, the mobility, the stability, the static weight, and the frontier heuristics of both parties based on the domain knowledge we researched for. The aims are to facilitate our agent in getting corners and stable pieces as much as possible throughout the game. While we adjust weights for each heuristic component dynamically, we focus on limiting the action our opponent can take while maximizing ours. With the static weights heuristic to guide the agent in the early game, it helps especially avoid placing pieces unintentionally near the corners that our opponent could take later, while focusing on getting as many pieces as possible in the later game. Throughout our Minimax development, the main challenge was to discover the critical heuristic components and their corresponding weights while we were having a lack of domain knowledge. We attempted to overcome those challenges by doing relevant research. For future improvements, we would like to consider balancing the heuristic measurements with some additional ones while making our agent more informed. Some heuristic calculations could be potentially optimized, while dynamically changing the depths could be considered to maximize the time usage. Here I'm going to demonstrate our final Minimax agent against our previous version, which doesn't contain the static weight heuristic. We can see that without static weight heuristic, the player could easily get into the state while potentially gives the corner to the opponent later in the game. Since it has no notion about how dangerous the squares around the corners are, and it doesn't know anything beyond depth 3 that we chose. Here is another demo of our final Minimax agent against the one without the frontier heuristic. We can see that the final agent tries to limit the number of pieces as much as possible, which meanwhile limits the action the opponent could take. It seems like the white party is about to win. However, at the end, they have no action but to pass, therefore giving a huge opportunity to our final agent to turn the game around. I will now pass to Zixing for our MCTS approach.
Hello, I'm Zixing. After introducing the first method, we can see that the disadvantage of that method is we need to design the situation heuristic function by ourselves. The design of this function is very difficult, so we tried the second method, which is the molecular tracers. This is a call for the algorithm. Molecular tracers can be roughly divided into 4 steps: selection, expansion, simulation, and backpropagation. The specific approach taken for the selection module is UCT strategy. It is a combination of MCTS with the UCB1 strategy, and UCB1 strategy is chosen because of its stability, flexibility, and simple mathematical formula. We use random rule-out strategy in the simulation part, and we do a little improvement here. That is, if a volley action contains any corner location, we would make it choose the corner place first. You can see here. Finally, when doing backpropagation and updating Q table and node visits, we will also try to use CSV file to record Q table and node visits so that we could get a more accurate value through training. Some challenges also are faced for this AI method. One of them is how to get a correct actions when expanding a new node. In the complex process of simulation, we have to make sure that every action is valid for the current state and players. So we solve it by saving the agent ID as an object variable. It's easy and clear to use. This AI method can overcome random AI 100%, but cannot defeat our first AI method. From this demo, white is MCTS and black is Minimax. We can notice that MCTS plays more randomly. It has no sense of occupying advantageous positions such as corners, and when the simulation is not sufficient, it will be more obvious. In future, we could improve the 3 aspects for MCTS. First one, our tree policy could be better instead of learning from scratch. Second one, the rule-out policy we use is also completely random, so we could do some optimization for this module. Final one, we could also optimize the reward. That's all for this video. Thank you everyone for watching.